Assalamu alaikum, dear students. In this video, I will discuss about the serial correlation. The approach of this chapter to the problem of serial correlation will be similar to that used in the previous chapter. So here we will also attempt to answer the same four questions like what is the nature of the problem, what are the consequences of the problem, how is the problem diagnosed, and what remedies for the problem are available. But before I go to the main concept, first we need to know what is time series. So time series data involve a single entry, like a person, corporation, or a state, over multiple points in time. Such a time series approach allows researchers to investigate analytical issues that can be explained very easily with a cross-sectional regression. For example, macroeconomic models and supply and demand models are best studied using time series, not cross-sectional data. The notation for a time series study is different from that of cross-sectional one. Our familiar cross-sectional notation is like this one. Until now we discussed this kind of regression, like yi is equal to beta 0 plus beta 1 x1i plus beta 2 x2i plus beta 3 x3i plus eta I, where I goes from 1 to n. But then a time series regression has one entity and t different time period. However, so we will switch to this notation like this, like yt is equal to beta 0 plus beta 1 x1t plus beta 2 x2t plus beta 3 x3t plus ei. Here t goes from 1 to t. Thus, similarly we can write down y1 is equal to beta 0 plus beta 1 x11, beta 2 x21, beta 3 x31 plus eta I. It refers to the observation from the first time period. And then y2, okay, beta 0 plus beta 1 x12 plus beta 2 x22 plus beta 3 x32 plus eta 2. It refers to the observation from the second period. Then yt is equal to beta 0 plus beta 1 x1t plus beta 2 x2t plus beta 3 x3t plus eta t. It refers to the observation from the t time period. So you can see that this is the example of the time series. So now the question is, what's so tough about that? Okay, all we have done is change from I to t and change from n to t. Well, it turns out that time series studies have some characteristics that make them more difficult to deal with than the cross-section. So the order of the observation in a time series is fixed. With a cross-sectional data set, you can enter the observation in any order you want. But with time series data, you must keep the observation in chronological order. Then, secondly, time series samples tend to be much smaller than cross-sectional ones. Most time series population have many fewer potential observations than do cross-sectional. And these smaller data sets make statistical inference more difficult. In addition, it's much harder to generate a time series observation than a cross-sectional one. After all, it takes a year to get one more observation in an annual time series. Then, thirdly, the theory underlying time series analysis can be quite complex, in part because of the problem mentioned just here. The time series econometrics includes a number of complex topics that require advanced estimation technique. Lastly, the stochastic error term in a time series equation is often affected by events that took place in the previous time period. This is serial correlation. So, this is the topic of our chapter. So, let's get started. Okay, in this slide I will discuss the pure versus impure serial correlation. First discuss this pure serial correlation. So pure serial correlation occurs when classical assumption number 4, which assumes uncorrelated observation of the error term, is violated in a correctly specified equation. If there is correlation between observation of the error term, then the error term is called the serially, that means they are said to be serially correlated. When econometricians use the term serial correlation without any modifier, they are referring to pure serial correlation. The most commonly assumed kind of serial correlation is first order serial correlation, in which the current value of the error term is a function of the previous value of the error term. You can see here that eta t is equal to rho eta t minus 1 plus ut. So this one eta t, this is the error term of the equation in question. Rho indicate the first order autocorrelation coefficient. Eta t minus 1, like this is the previous year the error term, and u, it indicate the classical error term. Okay, this one. The functional form of this equation is called the first order Markov scheme, and the symbol rho, it is called the first order autocorrelation coefficient. It measures the functional relationship between the value of an observation of the error term and the value of the previous observation of the error term. So now here the magnitude of the rho, okay, it indicates the strength of the serial correlation in the equation. If suppose rho is 0, then there is a serial correlation because eta t would be equal to u, a classical error term. As rho approaches 1 in absolute value, the value of the previous observation of the error term becomes more important in determining the current value of eta t, and a high degree of serial correlation exists. For rho to be greater than 1 in absolute value is unreasonable because it implies that the error term has a tendency to continually increase in absolute value over time. As a result of this, we can say that this rho, it is greater than negative 1, but it is less than positive 1. So the right sign of the rho, it indicates the nature of the serial correlation in the equation. A positive value of rho implies that the error term tends to have the same sign from one time period to the next. This is called the positive serial correlation. So a negative value of rho implies that the error term has a tendency to switch signs from negative to positive and back again in consecutive observation. This is called negative serial correlation. Now you can see in this figure that with first order serial correlation, the current observation of the error term tends to have the same sign as the previous observation of the error term. An example of the positive correlation, okay, would be external shocks to an economy that take more than one time period to completely work through the system. And in this figure, you can see that with no serial correlation, different observations of the error term are completely uncorrelated with each other. Such error terms would conform to classical assumption number 4. That means this here, it doesn't violate the classical assumption number 4. But here in this figure, you can see that with negative first order serial correlation, the current observation of the error term tends to have opposite sign from the previous observation of the error term. In most time series application, negative serial correlation is much less likely than the positive serial correlation. So now what is impaired serial correlation? By impaired serial correlation, we mean serial correlation that is caused by a specification error such as an omitted variable or an incorrect functional form, while pure serial correlation is caused by the underlying distribution of the error term of the true specification of an equation and which cannot be changed by the researcher. But impure serial correlation is caused by a specification error and that can be corrected. To see how omitted variable can cause the error term to be serially correlated, suppose we consider this equation where y equal to beta 0 beta 1 x1t plus beta 2 x2t plus eta t, where eta t, this is the classical error term. If suppose x2 is accidentally omitted from the equation or suppose there is no data available for x2, then we run this regression y equal to beta 0 plus beta 1 x1 t plus eta t star, where eta t star is equal to beta 2 x2 t plus eta t. Thus the error term in the omitted variable case is not the classical error term eta t anymore. Instead, it's also a function of the one of the independent variable x2. As a result, the new error term eta t star can be serially correlated even if the true error term eta is not. In particular, the new error term eta t star will tend to exhibit detectable serial correlation when x2 is itself serially correlated. This is quite likely in the time series and the size of the eta is small compared to the size of the beta 2 x2 bar. So these tendencies hold even if there are number of included or omitted variables. Therefore, eta t star is equal to rho eta t minus 1 star plus ut. Another common kind of impure serial correlation is caused by an incorrect functional form. Here, the choice of the wrong functional form can cause the error term to be serially correlated. Let's suppose the true equation is polynomial in nature like this. Yt is equal to beta 0 plus beta 1 x1t plus beta 2 x2 x1t square plus eta t. But instead we run this regression, okay, a linear regression, yt equal to alpha 0 plus alpha 1 x1t plus eta t star. So here this new error term eta t is now the function of the error term eta and of the differences between the linear and the polynomial functional form. Now we can see in this figure that these differences often follow fairly autoregressive pattern. That is, positive differences tend to be followed by positive differences and the negative differences tend to be followed by the negative differences. As a result, using a linear functional form when a nonlinear one is appropriate will usually result in positive impaired serial correlation. So you can see in this figure also that the use of an incorrect functional form tends to group positive and negative residual together and causing positive impaired serial correlation.